I would like to start with some basic rules of the classical probability theory. What is a probability? A probability is a number between 0 and 1. And it refers to a statement, a proposition, or an event, whatever. Yeah? This is a proposition or an event, statement. And whenever there's a statement of which you are not sure whether it's true or not, you can assign to that statement a probability. And that's, to start with, just a number between 0 and 1. Already at this point, there's a lot of debate what a probability is. What you've probably learned at school is that probability is sort of the limit of a relative frequency. So you have a fictitious random experiment and you repeat it infinitely many times, and then the relative frequency with which a certain event occurs is then identified with the probability of that event. But of course this is a very idealized and hypothetical scenario. If I tell you the probability that it rains tomorrow is 20%, there's only one tomorrow. There's not 10,000 tomorrows that you can repeat, and then you measure the relative frequency and you determine the probability. It just happens once. Or if you write an exam, and then you can ask yourself, what's the probability that I will pass the exam? That's a very subjective judgment. It's not the result of a random experiment. And in fact, you don't need that. You can develop the whole apparatus of probability theory simply by saying this is a number between 0 and 1. And there are certain consistency requirements, how you work with probabilities, how you combine probabilities. That's the important thing. And then it turns out when you apply these rules consistently, then if you are in a situation where you can repeat an experiment many times, then it turns out that probabilities do in fact coincide with this limit. But you can work with probabilities also when you don't have the possibility to do these random experiments. That's a subject in itself. It becomes almost philosophical, and I don't want to get into that. I just want to show you the basic rules for working with probabilities. One rule is the normalization of probabilities. When you have several propositions, statements, AI, and you know that exactly one of them is true and all the others are false. So they are mutually exclusive. When one proposition is true, then the others are false, and one of them is true. So they are mutually exclusive, and one of them must be true. Mathematically, this means that proposition AI and proposition AJ, so that's the logical AND. Now this is always false for all I different from J. This is the mathematical expression for this mutual exclusion. Yeah, two different propositions out of the set cannot be simultaneously true. And the other statement that one of them must be true, I can write this in the following form, that this is the logical OR. I do the logical OR over all propositions in the set. Then this gives the statement which is always true. Now, when you have this situation, then the probabilities for all these different propositions must add up to 1. So then the sum over I, probability AI, must be equal to 1. This is the normalization. There's a closely related statement which sort of generalizes that. Let me in fact call this 2a and then 2b, that is called marginalization. And this says that when I have sum over I probability that AI and some other statement B are true, and again the AIs satisfy the properties that I wrote down above, mutually exclusive, one of them must be true, and B is an arbitrary statement outside of the set, any other statement, then this sum must equal the probability of B. This is called, this generalizes the normalization condition and is called marginalization. Then there's another property called the product rule, and it says that the probability for A and B, now here A and B are arbitrary statements, arbitrary propositions. This is given by the conditional probability that A is true given that B is true times the probability of B. Now this product rule, you can write that in two forms. You can either write it in this form, probability of A given B times probability of B. You could also write it as probability B given A times probability of A. Because the probability of A and B, you can exchange A and B. The order doesn't matter when you have a logical AND. So you could also write on the right-hand side probability of B given A times probability of A. And then you can equate, you can set these two possible forms of the right-hand side, you can set these equal and solve for example, probability of A given B, and you find that this is equal to probability of B given A times probability of A divided by probability of B. And this is, let me give this a separate letter, this is the so-called Bayes rule. And this is an extremely important and useful rule, and you will need that rule also to solve some of the problems on your first problem set. Okay, then next I would like to give you a very simple example to illustrate how probability theory can make quasi-certain predictions. That's what I claimed at the beginning, that even though you know almost nothing about the microscopic world, you can make quasi-certain predictions about macroscopic properties. I would like to illustrate that with a very simple example from statistics. And this simple example are coin flips. So you have a coin, you flip a coin, and you have either heads or tails, and you do this many times. You do this n times. And the catch is that the coin might be biased. So it's not necessarily a fair coin. It's not probability 1/2, 1/2 for heads or tails, but it can be an arbitrary probability distribution. So you have a coin, that's possibly biased, and the probability for heads is equal to p, and p is an arbitrary value. Now you flip this coin n times, so if n coin flips, and then you observe heads m times. This means that the relative frequency with which heads occur is the ratio m over n. And now I ask, what is the probability, given that I flip the coin n times, and given this probability for heads, p, what is the probability that in these n coin flips I observe relative frequency f? How do I calculate that? If I have a specific sequence of results, so I have a series, heads, heads, tail, 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 heads, tail, tail, and so on, for such a specific sequence, when heads occurs m times, then and tail occurs n minus m times, then the probability for this specific sequence is p to the power m times 1 minus p, that's the probability for tails, to the power n minus m. But now I'm not interested in the order in which heads and tails occur. So I have to, this is the probability for one specific order. But now I have to multiply with the number of permutations of the order that sort of maintain the frequencies of heads and tails, but just sort of permute the order in which the results occur. And now the number of permutations is the total number of flips, n factorial, divided by m factorial and n minus m factorial. This is the probability for observing m times heads, and therefore a relative frequency f, in n coin flips. Now we say the number of coin flips is large. And this allows us to employ a very useful formula that we will encounter several times in this course, namely Stirling's formula for the factorial. It's a formula for an asymptotic formula for n factorial. That's asymptotically for large n. This is n to the power n times e to the minus n times the square root of 2 pi n. This is the Stirling formula. It holds for large n asymptotically. And of these three factors, the first two factors dominate. So if you want to approximate this even further, then you simply omit the last of these three factors and you focus on the first two. So for very, very large n, asymptotically to good accuracy, it's just n to the n times e to the minus n. When we use that, then the n factorial in the numerator becomes n to the power n, e to the minus n. The m factorial, so first we use that m factorial is asymptotically m to the power m times e to the minus m. And then we insert for m, we insert f times n. And this gives us then f to the power m times n to the power m times e to the minus m. So I wasn't quite consistent. In some places I left the m, and in some places I replaced m by f times n. We can do the same for n minus m factorial. We use Stirling again, and we also use the fact that n minus m equals 1 minus f times n. So here we find 1 minus f to the power n minus m. Then we have n to the power n minus m, and then we have e to the minus n minus m. And we still maintain p to the power m and 1 minus p to the power n minus m. And you see that a number of terms cancel. You see that e to the minus n cancels against e to the minus m times e to the minus n minus m. You also see that n to the power n cancels against n to the power m times n to the power n minus m. And what remains is p over f to the power m, and now I write m as n times f. And then 1 minus p over 1 minus f to the power n times 1 minus f. And this finally I would like to write in the form that is e to the minus n times, and now I introduce a new quantity which I call sfp, with the double vertical line between the f and the p, which is defined in the following way. This function, that is f times log f plus 1 minus f log 1 minus f minus, and then in a square bracket, f log p plus 1 minus f log 1 minus p. So we have done just some algebraic manipulation here. We've employed Stirling for large n. And remember, we are still looking at the probability that we observe a certain relative frequency for heads in n coin flips if we are given the probability for heads. And it has this form e to the minus n times this new function s. Let's look a bit more closely at this function s of f and p. It's a function that you will encounter again in statistical mechanics. That's why I introduced it already here. If you consider p as a given and f as the variable, you can ask, where does this function have an extremum? So you can ask, where does the derivative of this function with respect to f vanish? At which frequency f does this function have an extremum? Now, when you look at the formula above, you take the derivative, you find that this is log f minus log 1 minus f minus log p plus log 1 minus p. And you see this expression vanishes exactly when f is equal to p. When f is equal to p, then the right-hand side vanishes. Then we can ask, is it the minimum, is it the maximum? So we look at the second derivative with respect to f. We find this is equal to 1 over f plus 1 over 1 minus f, which we can also write as 1 over f times 1 minus f. Now the relative frequency f is always between 0 and 1, and therefore this is always a positive quantity. So the second order derivative is positive, and therefore the extremum is a minimum. Now, what is the value of this function s at this minimum? The value of the function, so at this minimum we have s fp is equal to s pp. Now, insert f equal to p in the formula for this function s, and you see the function s vanishes. It's 0. So what do we learn? We learn that this function s has a minimum when the observed relative frequency equals the probability, and at this minimum this function has the value 0. Everywhere else this function s must be larger than 0. Yeah? So this also implies that s fp is larger than 0 for all f different from p. Now we can Taylor expand this function around the minimum. We can say s of f and p, this is approximately the function at the minimum, but at the minimum the function is 0, plus f minus p times the first derivative at the minimum, but the first derivative is also 0. So the first term, the first non-vanishing term that contributes to the Taylor expansion is the second order derivative. We have 1/2, and then the second order derivative, we found that above, that's 1 over f times 1 minus f. At the minimum, f is equal to p. So we have 1 over p, 1 minus p, times f minus p squared. Yeah? So this is to second order. Now remember, the probability for observing relative frequency f in n coin flips, given the probability p for heads, that was asymptotically, so with Stirling's formula, asymptotically this was e to the minus n times this function s. When we use this Taylor expansion around the minimum, this is e to the minus 1/2 n over p times 1 minus p times f minus p squared. This is a Gaussian. E to the minus times the difference squared. This is a Gaussian distribution. It's a Gaussian that has its peak at f equal to p, and the width of this Gaussian Remember the form of the Gaussian, that's e to the minus 1/2, and then you have f or x, whatever your variable is, minus the expectation value. In this case, this is p squared, and then divided by the standard deviation squared. So the standard deviation squared, or the variance of this Gaussian here, is p times 1 minus p divided by n. So the variance of the Gaussian goes like 1 over n, or the standard deviation goes like 1 over the square root of n. So the width of the Gaussian is of the order 1 over the square root of n, and this obviously goes to 0 as n goes to infinity. And here we have it. Here we have this quasi-certain prediction. That's what I mean by quasi-certain. If we repeat the coin flips many, many, many times, then the statement that the relative frequency of heads will be equal to the probability p, this statement becomes quasi-certain because the fluctuations around the expected value p become smaller and smaller. They are of the order 1 over the square root of n. Now this is, are there any mathematicians in the audience? The mathematicians probably know that. This is, of course, related to the central limit theorem. This is a generic feature that in the limit of infinitely many trials in a random experiment, you will approach a Gaussian and that becomes smaller and smaller. So, the statement that f is equal to p that's what I mean by a quasi-certain prediction. And this is a prediction of the kind that we will encounter in statistical mechanics. Yeah? There we have microscopic bodies, many constituents. We look at averages over these many constituents, and we can make, about these averages, we can make quasi-certain statements, quasi-certain predictions in the sense that I tried to illustrate here. I would like to, just without proof, I would like to generalize some of the results that I showed you for the coin flip experiment. I would like to consider an arbitrary random experiment, and each random experiment has one of, say, d possible outcomes with a probability distribution pi, where I goes from 1 to d. And of course they must sum up to 1. So sum over I pi is equal to 1. Now we repeat this random experiment n times. So we have n trials. And then we can ask in the same fashion as before, we can ask what is the probability given that we perform n trials and given the probability distribution for the outcomes, pi, what is the probability that in these n trials we will actually observe relative frequencies for these various outcomes, fi. So these are the observed relative frequencies. Now it turns out you can do the same reasoning as for the coin flip, and you find that asymptotically for large n, this has the form e to the minus n, and then a function s, which depends on the distribution of the relative frequencies and the probability distribution. And it's defined in the following way. It's the sum of I goes from 1 to d, fi log fi divided by pi. And this function has a name. It's called the relative entropy. So it's the first occasion where the term entropy appears. It's not identical with the thermodynamic entropy yet, but it's closely related. It's called the relative entropy. And it has, the relative entropy has properties analogous to the properties that we found for the coin flip case. The relative entropy of F, let me write this maybe in vector notation, it's a bit shorter, F and P, is always greater or equal to 0. And it's equal to 0 if and only if Fi is equal to Pi. So it's the same, you find the same as for the coin flip case. This function vanishes if and only if the observed relative frequencies coincide with the probabilities. Near the minimum, you can again Taylor expand. So this is of the order F minus P squared. So again, when you insert this expansion in the asymptotic expression above for the probability of a certain distribution of relative frequencies, again you find this Gaussian shape, only that it's now a higher dimensional Gaussian. It's not a one-dimensional Gaussian. You draw the same conclusion as in the coin flip case, that as the number of trials increases, it becomes quasi-certain that the observed distribution of relative frequencies equals the probability distribution, just like in the coin flip case.